Hi, my name's Emmy O'Donnell, and this is my STK Assignment 1. So we're going to start by inserting a satellite that we can use. We're going to switch this is for part A. This is going to be the separate satellite. Switch to astrogator. Let's do Keplerian coordinate type. Switch all these to 0. And because our altitude is 500 kilometers, our new orbit will be at 6878 kilometers. So that is our initial state. Now we are going to propagate our orbit. We do not need to propagate it that long, so let's just do this. And rename that to propagate to hours. Now that we have that, we need to add a target sequence, my bad. And inside that target sequence, we need to add a maneuver. I'm going to call that maneuver dv1. This needs to become a thrust vector. You need to make sure that you are a impulsive maneuver type. And because we're here, we're just going to be working in the x-axis. There we go. Radius of apoapsis. Okay, we need to go here. You should use both of these. We want our radius of apoapsis to be at 8378 kilometers, which is a altitude of 2,000 kilometers. Okay, so now we have our target sequence and our first. So now we need to propagate again. We are to propagate this one to apogee. So right here, apoapsis, get rid of duration. Let's call this to apogee. We'll change the color. We will make this one pink. Let's go back up here. Make this one blue. Okay, now that we're going to be at our apogee, we're going to want to do our target sequence. Here, let's rename these two. Begin Homan. Finish Homan. There we go. Let's add another maneuver to do our second impulse. So this will be named dv2. Let's do a thrust vector. And this is once again just going to be in the x. And we are concerned with our eccentricity this time. Okay, so let's go in here. Click use for both of these. You want our eccentricity to be 0. And we may have to come back and change our convergence for these. Okay, now we have both of those. We are going to go to our ascending node, so we need to propagate. Pull it out of there. I'm going to call you to ascending node. Make this the next color. Go here, ascending node, can remove duration. And now we need to do our plane change. Simple plane change. Let's add a maneuver inside of it. Call you dv3. Once again, it's going to be a thrust vector, and this one is going to be in the x and the y. We need to make sure we update mass based on fuel for all these. Back to dv3. Now we are concerned with inclination and eccentricity. Okay, go up here. Use all of these. We want our eccentricity to be 0. But now we want our inclination to be at 45 degrees. 45 degrees. Okay. And now finally, we are just going to propagate again. So we have our orbit. Let's just call it seconds. I'm going to change you to propagate 36 hours. Let's make this red. So that is our first sequence. Let's rename this satellite. This is going to be part A. Call it separate. So now when we run the sequence, we should be able to see what happens over time. Which it looks like we did not converge. So let's change all of that. Maybe need to run all active profiles, that'll help too. Running active profiles, we're going to apply everything we just did, and we're going to run again. 3D graph, let's reset. So you can see our initial orbit, our transfer, and then our inclination change. We're actually upside down right now, okay? Let's reset and run. Let's begin the Hohmann transfer. Now it has done the inclination change. So that's the first satellite. For part A, now let's insert a new satellite and do the combined transfer. An astrogator Keplerian starting at 6878 0 0. Okay, let's propagate for 2 hours again. How we started last time. Just go to properties actually. Propagate 2 hours. Now let's get our first transfer in here of our target sequence. This will add a maneuver. Trust vector once again just in the X. And we are interested in radius of apoapsis. Let's go here. We want our radius of apoapsis to be 8378 kilometers. Change our convergence. Run active profiles. Let's call you DV1. And remember to update mass based on fuel. Okay, now we got that. We're going to go to apogee again. Go to apogee, we're up to pink. To apoapsis. Remove duration. Start our new target sequence. So this was our first burn. And so now this one, we are going to be doing our second impulse for the for Helmut transfer, and we are going to begin the inclination change. So we're interested in eccentricity and inclination. dv2. (45°), bar convergence, and we're going to run active profiles. Now one more time, we are going to propagate 36 hours, and we can call this yellow. Now we have all this. Let's call this begin transfer begin inclination change. So now when we run this sequence, look at our 3D graph, we should see here's our starting orbit, here's our moment transfer, and our combined inclination change. And we can turn on orbital elements too if we would like to check. You can see we're at our initial orbit, be our transfer, now we're at our final orbit, and our inclination is 45 degrees. We check out our separate stage, initial orbit, our helmet transfer orbit, and our inclination change. But now we're curious about the change in delta V. So we can go up here, go to summary, and see that our delta V magnitude 362.52 meters per second, and this is for delta V1. For delta V2, we're getting 0. And for delta V3, we're getting 5,508.33. So that's 5,870 meters per second for separate. Now let's switch to V combined. So here we go, we did 362.52. And our delta V2, 5,167.27. So when you compare the separate to the combined, you end up saving 71 meters per second by doing the combined transfer. And that is part A of the assignment. Okay, so now part B is finding the lifetime of a satellite using the conservative lifetime, which means we're going to use the max altitude density we can have, and we are going to use the minimum and max frontal cross-sectional area. So opening up Excel, after some calculations, you can find that your area max comes out to 0.0424 meters squared, and your area minimum comes out to 0.01 meters squared. Now here is all the altitudes and the scale heights and max densities, which comes from the chart that was given to us. You calculate your ballistic coefficient by doing your mass divided by your area times your drag coefficient, which we're using 3 in this case. And that takes you into finding our delta A for our revolutions, which is this equation. And once you solve for that, our lifetime is just our scale height, our negative scale height, divided by our delta A rev. Now we're going to find the period of the satellite. So that's because lifetime is in revolutions and period is in seconds per revolutions. And so when you multiply for lifetime times the period, you end up with lifetime in seconds, which you therefore can convert seconds into years to find our desired altitude. So now this is so now we do not get our exact 5 years lifetimes that we want. So you have to interpolate with the altitude and the lifetime to find where your lifetime is 5 years. So once you do some math, you end up getting 7,062 kilometers for a lifetime of 5 years for our max frontal area. For our minimum frontal area, it is the same steps, but this time our minimum frontal area is 0.01 meters squared, and our ballistic coefficient is 116.6667. So once you use all the same steps for the max altitude, you end up interpolating and you find that your altitude is 7,060.83 kilometers. And that is part B. Alright, so now for part C, we're going to be using the altitudes we found in B, which ended up being 7,062.05 kilometers for our max frontal area and 7,060.83 kilometers for our minimum frontal area, using the 3 CubeSat models, 1976 Standard, the Jackia 1970, and the Jackia Roberts. So opening up STK, we're going to close all these. Now we're going to insert some new satellites. To make all this 0, we now have our altitude. We're going to do all of our max first. 062.05, 0 degrees. This should be on the HPOP. Okay, we're going to apply this. We're going to rename you C underscore. We're going to start with the 1976. This will be the max. So when we go in here, satellite, lifetime, we are able to change some settings around. See our frontal area is 0.0424 meters, and our mass is 3.5 kilograms. This will be the 1976 standard. We're going to compute, and our orbit time is 31.2 years. Let's add our next satellite. Let's go to HPOP. This will be our minimum. Apply, close. Let's rename this one. This will be the 1976 minimum. Satellite, lifetime. Change our numbers around. So this time our drag area 0.01 meters squared. Mass is 3.5. 1976. 9. Okay. Compute. This time our lifetime is 137.7 years. Let's add our third satellite. Now we're on to the 1970 model. This will be our max area. And for this one, our lifetime is 51.2 years. Let's do that same process but with our minimum. So 0.01 meters squared, 2.5 kilograms. We're in our 1970 model. Okay, so let's add some more iterations. So we see that this one will decay in 230.9 years, which does not sound very accurate to me. So finally, we are going to be on our last model. So let's do our maximum. This will be using the Jackie Roberts. So I'll call it JR. So 0.0424, 3.5. So advanced, add some more orbit counts and switch to the Jackie Roberts atmospheric density model to compute it. 44.8 years. And one more satellite. At our minimum altitude. Rename it to C. Jackie Roberts minimum. Calculate the lifetime. Add some more orbits. Switch to Jackie Roberts model. Compute. This one will decay in 207.6 years. And that is the end of Part C. So for Part D, we were asked to investigate the effect of inclination angle and solar flux levels on the lifetime from the highest altitude we found in part B. So the highest altitude we found in part B was 7,062.05 kilometers, which that is our radius of Appalachia, so our real altitude is 2,000 kilometers. But accounting for the radius of the Earth, you end up here. So using the Giacchi-Roberts model, I plotted the inclination angle, solar flux, and found the lifetime. So when you compare lifetime and solar flux, it appears that solar flux has a linear effect on lifetime, and this is because when there's more sun activity, the the, the atmosphere is heated up, the particles are energized, and so the particles rise up higher into the atmosphere, which creates more drag for the satellites. And on inclination angle, you can see the lifetime decreases at 45 degrees, but then again starts to increase around 75 degrees. So this is because towards the poles, which would be the inclination angle of 90 degrees, the poles are flattened, so you end up gaining about 21 degrees of 21 kilometers of altitude. And due to Earth being an oblate spheroid, you end up losing altitude at 45 degrees. So when you plot, so when you compare all these values and you sort the lifetime from largest to smallest, you see that you have the largest lifetime at 15 degrees, 0 solar flux, and the lowest lifetime at 45 degrees and 3 for solar flux. And that is the end of part D. For part E, we were asked to graph the 1-year perturbation effects of the RAN, argument perigee, eccentricity, and inclination angle using the H-pop propagator. So we're going to start up STK, and we are going to run it for 1 year. We are going to insert a satellite using the orbit wizard. We can call this part E, Molniya orbit. And our type is going to be Molniya. We're going to apply, hit OK. So now we have our orbit, and we can see here, and we are trying to graph. So let's right click, go to Report and Graph Manager, and we are going to specify time properties. We want our set time to be 1 day. We are going to create a new graph style. Let's just call this E Molniya. Open it up. Go down to classical elements. Add eccentricity here, inclination, RAN, and argument and perigee. Set our step size to be 1 day. Apply. Okay. Now we can generate this graph. And we can see the argument of perigee is unchanging. The inclination is unchanging. The RAN is decreasing over time. And the eccentricity is not changing either. And that is the end of part E.